Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about this problem. So let's get started. The problem is given as you are given two numbers and you have to find GCD or HCF of two numbers. GCD stands for greatest common divisor and HCF stands for highest common factor. The meaning of both the terms are same. Let's understand this with an example. Let's say we have two numbers 12 and 33. All the divisors of 12 are 1, 2, 3, 4, 6, 12 and divisors of 33 are 1, 3, 11 and 33. Now, what are the common divisors among all of these divisors? 1 and 3 are common in both the 12 and 33. And out of 1 and 3, 3 is the greatest common divisor. So we can say that the greatest common divisor of 12 and 33 is 3. It means this is the greatest number that divides 12 and 33 both. Alright, let's move on. So let's see some more examples. So in case of 4 and 6, the GCD of 4 and 6 is 2. In case of 9 and 10, the GCD is 1. Even though 9 and 10 are not prime numbers, but they do not share in common factor. Next, in case of 7 and 12, here 7 is prime number. So the GCD of 7 and 12 is 1. Because there are no common greatest factor among 7 and 12. Now here we have observations to be made. You can see in all the GCDs, the GCD exists between 1 to less than equal to minimum of A and B, right? So here 2 is less than equal to 4, here 1 is also less than equal to 9 and here 1 is also less than equal to 7, right? So it means our GCD of any number exists between 1 to minimum of A and B. So let's use this idea and implement in our code. So here you can see a brute force approach to solve this problem. In this code, first we are finding minimum of A and B and then we are running a loop in reverse order till GCD greater than 1. And in each iteration we are checking if both the numbers are divisible by GCD or not. If we find that number, we immediately return the GCD. So let's see with an example. Let's say we have two numbers A is 7 and 12. The minimum of 7 and 12 is 7. So we are going to start our loop from 7. And we decrement this number by 1 and in each step we check if our A and B is divisible by this number or not. And when we found that number, we simply returns. So at first the value of GCD is 7. We decrement to 6, we decrement to 5, we decrement to 4, then 3, then 2, then 1 and then 0. So it means in all the cases we are not able to find any number that divides 7 and 12. When GCD becomes 0, our condition becomes false and we come out of this loop and we simply return 1. Now let's see with another example. Let's say the value of A is 6 and 4. So the minimum of 6 and 4 is 4. We start our loop with 4. We check for 4, then we decrement 4 to 3, we check if 3 divides 6 and 4 or not. If not, we simply decrement 3 to 2 and in case of 2, we check if 2 divides 6 and 4 or not. So in case of 2, 2 simply divides 6 and 4. So it means we simply have to return 2. It means 2 is the GCD of 6 and 4. Now let's talk about time complexity of this function. So how many times our loop is going to run? So we can clearly see that our loop is going to run from minimum of A and B till 1. So it means the time complexity of this function comes out to be big O of minimum of A and B. So far so clear. So this is the brute force approach to solve this problem. So in this approach we can see that the time complexity is too much. So can we reduce this time complexity? Do we have a better approach to solve this problem? Can we make this code more efficient? Yes, we do have a better approach to make this code more efficient. And this is where our Euclide's algorithms come into picture. This is the algorithm which is used to calculate the GCD of two numbers. And this algorithm is named after the ancient Greek mathematician Euclides, who first described this algorithm. And this is the oldest algorithm used to find GCD of a number. So let's see what this algorithm has to say. The algorithm says let A and B are two numbers such that B is smaller than A, then the GCD of A and B is going to be GCD of A minus B, comma B. Let's see with an example. Let's say we have two numbers 8 and 3 and we need to find GCD of 8 and 3. So as per the algorithm, the GCD of 8 and 3 is going to be GCD of 8 minus 3 and 3, right? And the condition is B should always be smaller than A. So here the 5 is larger and 3 is smaller, so that is correct. So now in next step, the GCD of 5 and 3 is going to be GCD of 5 minus 3, it means 2 and 3. Now here 3 is larger and 2 is smaller, so we swap the A and B in next step. So now GCD of 3 and 2 is GCD of 3 minus 2, that is 1 and 2. And then the GCD of 2 and 1 is going to be GCD of 1 and 1. And this is our stopping condition. It means when A is equal to B, then we simply return the value of A, and that is going to be our GCD of 8 and 3. Clear? Now let's see the implementation of this algorithm in code. So on the right side you can see this is the basic implementation of Euclid's algorithm. What we are doing here, we are simply running a loop till A equals to B. And in each iteration we are checking if A is greater than B, then we are subtracting B from A. And if B is greater, then we are subtracting A from B. And this way we reach to a condition where A becomes equal to B. At that point we come out of this loop and we simply return the value of A. So in case of 6 and 4, so in first iteration the 6 is greater than 4, so we subtract 4 from 6. So we get A equal to 2 and B equal to 4. In next iteration 4 is greater, so we subtract 2 from 4. So A becomes 2 and B becomes 2. So at this point our A and B both are equal, so we get out of the loop and 2 gets printed on the screen. Alright, so now let's talk about the time complexity of this function. So as we are running loop here, so we can say that in worst case, if A is equal to n and B is equal to 1, we are going to run this loop n minus 1 times, correct? Because here I am assuming that if B becomes 1, we are running loop from n minus 1 time. So the time complexity of this code is going to be big O, and it is a linear growth of algorithm. So far so clear, great. Moving on, we even have one optimized solution of this problem, and that is where we are going to use recursion. So in this code we are using recursion, and this code is based on long division method. So let's see with an example. Let's say we have 8 and 3 and we have to find GCD of 8 and 3. So what we do, we divide 8 by 3, we get some remainder. Now, and the remainder is 2. Now we again divide 3 by 2, we get remainder 1. And we again divide 2 by 1, we get remainder 0. So basically what we are doing in long division, we divide number till we reach 0. And this is a form of recursion. See, the GCD of 3 and 8 is same as GCD of 2, 3 is same as GCD of 1 and 2. So we are using recursion here and we are using long division method. And this optimization is based on both the concepts, right? One more thing to notice here, that in this recursive call, what is happening, the remainder becomes divisor and our previous divisor becomes dividend. So here, right now the divisor is 3 and the dividend is 8. After dividing 8 by 3, we get 2. Now 2 is the remainder. So remainder becomes divisor. So remainder become divisor, and the previous divisor, that is 3, becomes dividend. So this is the process we follow in this approach. So now if we have to write the recurrence relation of this function, we can write GCD of A and B is equal to GCD of B, comma A modulus B. So let's understand this with example. Let's say in case of A equal to 8 and B equal to 3. So we call this function by passing 8 and 3 in place of A and B. So this function makes a recursive call to itself by making A equal to 3 and B is going to be 8 modulus 3. In next iteration, our 3 is going to become dividend and the remainder is going to become divisor. You can see here that here is 3 is dividend and remainder is 2 is remainder. And in next step, in next recursive call, our 3 is going to become dividend and 2 is going to become divisor. And this process continues, and we stop when b is equal to 0. And at that point we simply returns 1. And at that point we simply returns the value of 1. So in case of 8 and 3, the greatest common divisor of 8 and 3 is 1. So let's see how recursion calls work. So we call this function by passing 8 and 3 to it. The 8 and 3 makes a recursive call to 3 and 8 modulus 3, that is 2. Okay. The GCD of 3 by 3 comma 2 makes a recursive call to 2 and 3 modulus 2. And GCD of 2 comma 1 makes a recursive call to GCD of 1 and 2 modulus 1, and that is 0. So this is where our b becomes 0, and we simply return control backs to parent call. And the parent of this is this, and parent of this is this. So this is how the control goes back to parent. And we get our answer, that is 1. Now let's talk about the time complexity of this recursive function. So how many recursive call we are going to make in this approach? In best case, if a equal to n and b equal to 1. So what happens when b is equal to 1? When we do modulo with b with any number, then that number becomes 0 and we simply comes out of loop, right? Now in worst case, what happens when a is equal to n and b is equal to 2? Our loop is going to run log n time. Why? Because the smallest number we can assume that b is equal to 2, right? And we divide number by 2. So what happens when you divide any number by 2? We divide that number into 2 parts. So in those type of scenarios, we are always going to have a time complexity of log of n. So that is why the overall time complexity of this recursive function is going to be big of log of n. Now so far so clear. I hope everything is clear. Now let's see some real world example of this GCD algorithm or Euclid's algorithm. Let's say you are constructing a room and the size of room is 6 feet by 4 feet. Now the challenge for you is that you are looking for maximum size of tile so that you can tile your room. So the answer could be 1, 2, 3, 4, but you are looking for a maximum size of tile so that it fills all the room, right? So this is where GCD helps you to calculate the maximum size of tile. So if you calculate the GCD of 4 and 6, it comes out to be 2. It means the maximum size of tile you need to tile the room is 2 feet. Means you need a tile of size 2 feet by 2 feet to fill all the room. And how many tiles you need? You need total of 24 tiles because the size of room is 66 by 4, 24 feet. So you need 24 tiles of 2 feet to fill the room. So this is how Euclid's algorithm help us to solve our problem. I hope now you have a solid understanding about how Euclid's algorithm works. So this is it for this video. Thanks for watching. See you in the next video.